Alright, welcome to our first in a series of hopefully 2 videos about something called vectors. This is another math topic, but it's one that you probably have not been exposed to yet. You've talked probably about the metric system in previous grades. You've talked about scientific conversion or scientific notation. You might have even talked about unit conversion at some point, or maybe very basic unit conversion, and even estimation. You probably haven't talked about vectors yet, okay? Or maybe you have and I'm wrong. But a vector, it's not a particularly difficult mathematical concept to know, but it is new. So let me start you off with this example. Let's say you go hiking, and on your hike, you hike like this. You walk 7 kilometers north, 4 kilometers east, and 4 kilometers south. Let's sketch a picture of that just to see what the route looks like. So here is the start. You go 7 kilometers to the north. We'll say that north is in this direction. Let's say you go 4 kilometers east, and then you go 4 kilometers back to the south. Okay, so 7 kilometers, 4 kilometers, and 4 kilometers. There's our picture. Now, I'm going to ask you 2 different questions here. The first is, how far did you walk? That's a pretty easy one. You walked 7 kilometers, then 4 kilometers, then 4 kilometers. 7 plus 4 plus 4, if you don't believe me, is 15. 15 kilometers. This measurement is called distance. How far an object moves over some period of time is called distance. The trickier question is this: how far are you from your starting point? You are not 15 kilometers away from your starting point. That's this right here. Okay, that right there is how far away you are from your starting point. And you might say, well, I have no idea how I calculate that, but think carefully about the geometry here. I know that you are, or we know that you are, let's see, 4 kilometers in the more farther east than you were when you started. You went 7 kilometers north and then 4 kilometers back south, so you must be 3 kilometers north of where you started. So I'm just going to draw this in right here. This must be a distance of 4 kilometers. And this section right here must be 3 kilometers. So I know that this is 3 kilometers because from here up to here, where the 4 kilometer arrow ends, that must be 3, so that this can be 3, and then 4 for a total of 7. So I have a 3 kilometers here, 4 kilometers here, and you've probably noticed that this makes a 3, 4, 5 triangle. If you didn't know that, you could do a squared plus b squared equals c squared. Since this is a right triangle, you realize that it's a right triangle, you do 3 kilometers squared plus 4 kilometers squared equals c squared. 3 squared is 9 plus 4 squared is 16, c squared. This is 25 equals c squared. And we get c equals 5 kilometers. So at this point, you are only 5 kilometers from your starting point, but you've walked 15 kilometers. How is that possible? Well, you didn't walk in a straight line, okay? The measurement of where you are from your starting point is known as displacement. Okay, displacement. That is how far you are from your starting point and in what direction. Some measurements that we make this year are known as being direction-dependent measurements. In other words, these measurements are incomplete if you don't say what the direction is. All right? So this displacement that I'm talking about, that is a direction-dependent displacement. Not only does it matter what direction I'm moving in, that influences how big the displacement is. In order to be very accurate, if I want to know how far I was from my starting spot, I should say I'm 5 kilometers and whatever angle, I could measure maybe an angle or say I'm some degrees north of east from my starting spot. It's direction dependent. Direction is important. These measurements that are direction dependent are called vectors. I'm going to define vector first. A vector is just a measurement that needs both magnitude and direction to be, in quotes, complete. Okay? Magnitude is just a fancy word for size. So it needs both the size of the measurement, in this case 5 kilometers, and the direction, some amount of degrees north of east. I'm not going to bother measuring right now. The opposite of a vector is a scalar. A scalar is a measurement that does not need a direction to be complete. It only needs a magnitude. So it only needs a size. Distance is actually a scalar because how far you walked is not really dependent on what direction you're moving, it's just the length of your path. Okay? Distance is simply the length of the path an object takes. Displacement is how far you are from where you began, how far the ending point is from where and whatever object started. That does depend on what direction you're walking, and in order to be complete, you should say the direction that you would move from the start to the finish if you were to go in a straight line. An example of a scalar measurement is mass. Mass is just a fancy word for how much matter is in something. So for instance, my mass, might be a little more now after the quarantine, is approximately 72 kilograms. There is no direction needed here. Okay, I don't have to say 72 kilograms east. It doesn't even sound right. It just sounds weird. All right. An example of a vector is a force. Now, we're not going to talk about force for about 2 more months, about another month and a half, but a force is a vector. You know this because a force is essentially a push or a pull on some other object. Depending on the direction you push or pull on something, that will change what happens to the object. For instance, if I push on the paper down right now, nothing's going to happen to the paper. But if I push this way on the paper, it moves. Force must be a vector because the direction of the force matters. If you push on something, the direction matters. Okay. We're going to mainly talk about vectors. There's a lot of scalars in this course too, but right now we're talking about vectors. When you draw out a vector, we draw vectors very often in this class. A vector just looks like an arrow. It must have an arrowhead on one end to indicate that direction. Since it's a vector, we need the direction. An example of a vector would be this. Now, I should have drawn it with my straight edge. Should have got the protractor in there to draw it. But no matter, this is a pretty good vector, okay? It has an arrow on one end to indicate direction. That's called the head. This is the tail of the vector. Here's another vector. Okay, I could draw tons and tons of different vectors. That's not really going to benefit you though. Let me draw some wrong vectors, some stuff I don't want you to draw. Do not draw your vector like this. And also, do not draw your vector like this. Of these two, I see the one on the right much more often. The whole point of a vector is that you are supposed to measure from the tail to the very tip of the head, the very tip, the very farthest part. And that's important. I'll talk about why that's important in a little bit. But that's how you're supposed to measure a vector. If you draw a vector like this, it's kind of unclear whether you're supposed to measure to here or to the end of the line. So don't do this. And don't do this either because, again, it's unclear if you're supposed to measure to here or to the actual tip of the head. Draw your vectors like this, with the arrow the farthest, the tip of the arrow being on the farthest part of the line. Okay, that's how you should draw vectors. Going off what I just said, the length of a vector, how you draw it, is its magnitude, or its size. Sometimes you're going to draw a vector that might represent a physical quantity, like a displacement or a force or any other vector. When you're doing this, a lot of times what you're going to have to do is to establish a scale so that you know how big to draw the vector. Okay? Say you're drawing a force vector. You have to establish a scale because a force isn't measured in meters. I won't even talk about what it's measured in right now. but you might need to establish a scale to show how big the force that you drew is. For instance, you might have to say something like, okay, well, if I drew a 2 centimeter vector and 1 centimeter equals 50 force units, my 2 centimeter vector represents 100 force units. The direction of a vector is measured between a vector and some sort of reference line. This is some line that's always in the same place that you can make reference to. The reference line can either be a compass rose, in other words, north, south, east, west in the normal spots, or an XY graph. This year we'll do a little bit with compass rose and a little bit with XY graphs, but most of the time we're going to be focusing on XY graphs, especially moving into AP next year. Let's practice drawing vectors right now. And this is going to be a little cramped on your sheet. Please make sure at this point you have a protractor. Okay, it's crucial that you have a protractor so that you can do all of this. If you need help getting a protractor, please let me know and we'll figure something out. Number 1, a 3 centimeter vector at 40 degrees north of east. So this is a little confusing. North of east can be a little confusing. There's a couple different ways how you can think about it. The 3 centimeters is pretty self-explanatory, but what does that 40 degrees north of east mean? Well, we know that on a compass rose, this is east and this is north, okay? So 40 degrees north of east, the way you're going to do this is you're going to line up the 90 degrees on the protractor with the first direction given, if you're given directions like on a compass rose. So that means you're going to line up 90 with north. You're going to line up the 0 with east. There's only one possible way to do that, and it looks like this. So now I have 90 degrees right here lined up with north. Oh, this is really bright. Okay, there we go. So now I have 90 degrees lined up with north, 0 degrees lined up with east. So you line up this number with 90, line up this direction with 90, line up this direction with 0. Now you measure 40 degrees towards north from east. East is out this way, so I start here. See, it says 0. I go up 10, 20, 30, 40. What I'm going to do is just make a little dot right there. That's my reference. Now, when I move back, I line that dot up with the origin along the lower part of my the inside of my protractor, and I draw in that direction for 3 centimeters. 1, 2, 3. I put an arrowhead on it, and I have just drawn a 3 centimeter vector 40 degrees north of east. If you're still a little confused about what the whole north of east thing means, think of saying this: to the north of east. 3 centimeters at 40 degrees to the north of east. What that means is, it's almost like it's telling you, start at east and to measure 40 degrees to the north of that. Okay, that can help you. The next vector we're going to draw is a 4 centimeter vector at 10 degrees west of south. West, south. Line up the first direction I'm given with 90, line up the second one with 0. There's only one way to do that. Okay? Now, you might see a little problem that I'm running into here. 10 degrees is down here, and it's running off my paper. Not to worry. Just take another piece of paper, put it under here. Make sure you don't move that paper, and mark a 10. Mark a spot at the 10. Then, without moving either paper, line up that spot with the origin. Oh, I got this backwards. I don't think I moved anything. Line up that spot with the origin, and draw a 4 centimeter long vector. Goes out to here. Okay, and that should be 4 centimeters at 10 degrees west of south. Let's see, is that about 10? I'm just checking for my own purposes because I'll go crazy if it's not. Okay, it's a little off, but it's pretty much 10. All right, so when you have a compass rose terminology and you're working with that, what you really want to do here is think of the second direction. Can you see this? Okay, for compass rose, the second direction is the reference line. That's what you're measuring from. Okay, so it says 10 degrees west of south. We measured from the south 10 degrees towards the west. 40 degrees north of east. We started at east, measured 40 degrees to the north of that. Okay, that's more useful probably in a real life setting. What we're also going to do is measure based on an XY chart or an XY graph. The third vector is 2.7 centimeters at 210 degrees from the positive x-axis. There should be a positive sign right here. Positive x-axis is this one right here. Here's the positive y, negative x, negative y. We know that starting from here, we call this 0 degrees, 90 degrees, 180 degrees, and 270 degrees. If we were to go all the way back around, this would also be 360. So we know, based on these that you've kind of had burned into your head through math classes, we're talking about a vector that's somewhere in this quadrant, quadrant 3, between 180 and 270, probably a little closer to 180. What I would do is, since we know it's between 180 and 270, I'm going to see what the difference between 210 and 180 is. 210 minus 180 is 30. So I need to get to 180, so my vector direction is past 180 by 30 degrees. So I'm going to line up the protractor with 0 on heading towards 180, aligned with 180, and I'm going to put a dot 30 degrees from that 0. There you go. Now I can trace out 2.7 centimeters. I know this is upside down. This is hard for me to read too. From the origin along that line. It should look something like this. Okay? So 2.7 centimeters at 210 degrees from the positive x-axis. The angle we're measuring is this one right here, this big obtuse angle. All right? So vectors are tricky. The more practice you get with them, the easier they become. All right? So when you get a chance to do the homework, I would do it in pencil, and I would be very careful about your drawings. If you have any questions, absolutely, please just let me know. I'm going to stop there. When we get to the back in a little bit, can you guys, yeah, you guys can see everything. When we get to the back in a little bit, what we'll be doing is measuring vectors instead of drawing them, and then I'm going to teach you how to add vectors, because that's really important in this class. All right, I'll see you soon.